Hello everyone, I am Mr. M. Vignesh. Welcome to this lecture on bipolar junction transistors, commonly known as BJTs. In the previous lecture we have learned about diodes. Today we will study another important semiconductor device, the transistor. A transistor is one of the most widely used electronic components. It can act as an amplifier, increasing the strength of the weak signals, or it can act as a switch controlling the flow of current in electronic circuits. Let's begin by understanding the base structure of a transistor. With respect to introduction, a transistor is a current controlled semiconductor device. It has three terminals called the base, emitter and collector. There are two main types of BJT, NPN transistor and PNP transistor. The emitter supplies charge carriers, the collector collects them, and the base controls the movement of these charge carriers. Because a small change in the base current can control a much larger collector current, transistors are widely used in amplification and switching applications. So this is the BJT structure. Let us now understand the structure of a bipolar junction transistor. A BJT consists of three semiconductor layers which form two PN junctions. The three terminals are emitter, base, collector. The emitter is heavily doped so that it can supply a large number of charge carriers. The base is very thin and highly doped. This allows most of the charge carriers to pass through it with very little weak combination. The collector is moderately doped and is designed to collect the charge carriers coming from the emitter. In an NPN transistor, the emitter and collector are made of N-type semiconductor while the base is P-type. In PNP transistor, the emitter and collector are P-type while the base is N-type. This figure shows the different transistor packages. When coming to the operation, we'll quickly go through the transistor structure again. In the diode, we have only one PN junction. However, in a bipolar junction transistor, there are two PN junctions. These are emitter junction, emitter base junction, which is also called as EB, and the collector base junction is also called as CB. These two junctions work together to control the movement of current through the transistors. You can think of transistor as two PN junctions connected back to back, but its operation is much more powerful than simply connecting two diodes. So now we'll go through the transistor operation. Before that, we will quickly go through the each and every transistor packages which you have seen just before. The transistors are available in different physical packages depending on their application. Small transistors used in electronic circuits are available in compact plastic packages. Power transistors are enclosed in larger packages that help dissipate heat effectively. Although their shapes and size may differ, the internal operation of all BJTs remains the same. The important thing is to correctly identify the emitter base collector terminals before using the transistor in a circuit. Now we will come to the transistor operation. Now let us understand how an NPN transistor operates. For normal operation, the transistor must work in the active region. To achieve this, the emitter base junction must be forward biased and the collector base junction must be reverse biased. The forward bias reduces the depletion region at the emitter base junction, allowing the electrons to move easily from emitter into base. Reverse bias at the collector base junction attracts the electrons towards the collector. This arrangement allows the transistor to amplify signals effectively. So let us see what happens inside the transistor in this slide. When the emitter base junction is forward biased, a large number of electrons leave the emitter and enter the base. Since the base is very thin and lightly doped, only a few electrons combine with the holes in the base. This recombination produces a small base current. Most of the electrons continue their journey towards the collector because collector base junction is reverse biased. As a result, large current flow is happening. This is why a small base current can control a much larger collector current. This property makes the transistor as an excellent amplifier. Now we'll see some parameters related to transistor current. This transistor currents, there are three important currents. One is emitter current represented by IE, and base current represented by IB, and collector current represented by IC. According to Kirchhoff's current law, the emitter current is equal to the sum of collector current and base current. In simple terms, emitter current equals collector current plus base current. Since the base current is very small, the collector current is almost equal to the emitter current. So that is what we are seeing it is in diagram with the equation. So now let's discuss about the current gain and alpha beta relationship. The common base current gain is represented by the symbol alpha and is defined as the ratio of collector to emitter current. This value is around 0.98 to 0.99. The common emitter current gain is represented by beta, whereas common base is previously we discussed as alpha. So it is also defined as the ratio of collector current to base current, whereas in case of common base, the denominator is emitter current. The value of beta is much larger than alpha, usually ranging from 50 to 300 depending on the transistor. Higher beta means a greater amplification capability. So this alpha beta are related to each other through mathematical equations. Although these equations are important for transistor analysis, the main concept is simple. Alpha is always less than 1 because the collector current is slightly smaller than the emitter current. Beta is much larger because the base current is very small. In practical circuit design, engineers often use the beta value because it directly indicates how much current amplification the transistor can provide. So these equations illustrate the relationship between the alpha and beta with respect to the KCL applied in the common emitter and common base configurations. Here we can see the values. So these are all some of the different transistor configurations. There are three transistor configurations available. One is common base, common emitter and common collector configurations. So these configurations are found based on the transistor terminals. So because the BJT has three terminals, that is emitter, collector and base. So assume that we are using this BJT for a two-port applications. One of the BJT terminals need to be made common between input and output. So according to the common terminal out of three, we are naming these configurations. So this is the circuit diagram for common base configuration, where input is common to base and emitter and the output is common to collector and base. So base is common for input and output. So this is called as common base. Next is common collector. We will quickly go through the configurations alone. In common emitter, you will see the collector later. In common emitter, emitter is common for input and output. The input forms base and emitter, the output forms collector and emitter. Next is common collector. In the common collector, the diagram is not present here. We will discuss the common collector configuration and its input output characteristics of all these three configurations in an elaborate manner in the next lecture. So I hope you understood the concept of transistor, how the transistor is formed with respect to the PN junction and what are the different types of transistors available and how these transistors are operated and how can we use these transistors for different applications by using the different configurations in this lecture. We will see in the next lecture. Thank you.